Hello, everybody. Welcome to the new session of our Quantep seminar. It's a great pleasure and honor, actually, to welcome Karl Jansen from DESY, who's giving the Quantep seminar today. So Karl Jansen is an eminent high-energy physicist with a lot of very important contributions to our understanding of QCD and lattice field gauge theories and high-energy physics in general. And recently, he's been very active also exploring the frontier between this field and quantum computation and tensor networks and the potential of this approach to address these field theory problems. So it's a great honor to have you, Karl, today. Thanks a lot for accepting to join our Quantep seminar. And please, the floor is yours.
Thanks a lot, Yasser, for this invitation. For me, it's a really great pleasure to talk here. And Yasser told me that you are mostly coming from quantum information theory. So I therefore really encourage you to interrupt me if you don't understand something or I should repeat something. It's not my intention that we necessarily go through the whole talk, but it's my intention that you really take something home. Okay, so don't be shy. Just ask me, and if I can answer, I will answer. And what I would like to do today is that I want to give you a possible way for using tensor networks and quantum computing in lattice field theory in the future. And for this, I will first discuss a 2+1 dimensional U1 gauge theory in the Hamiltonian formulation, and I will show you how we are thinking of truncating the theory in the degrees of freedom, and how we can map from the electric to the magnetic basis to really cover the whole parameter range. And then I want to discuss also the Hamiltonian formulation for the 3+1 dimensional U1 gauge theory. And in particular, I will show you how you can formulate a topological term for the Hamiltonian in 3 space dimensions. And once we have this Hamiltonian formulation of the topological term, this opens the path for classical calculations, so tensor networks, and also quantum calculations on the quantum computer for topological questions. But let me first, okay, now it doesn't page, it does. But let me first come to this 2+1 dimensional U1 gauge theory. You see here the collaborators, Jan Haase, Luca Dell'Antonio, Alessio Celi, Danny Paulsen, Angus Kahn, and Christine Muschig, and it's published in Quantum. So we start with the lattice Hamiltonian. We have a lattice spacing A, and we have periodic boundary conditions. And the gauge Hamiltonian consists of an electric part and a magnetic part. And in the electric part, we have the electric field operators at the point N in direction either X or Y. And in the magnetic part, we have the plaquette operators, which are given here. And this is all multiplied with G square for the electric part and 1 over G square for the magnetic part. Now, the electric field operator, this simply gets eigenvalues of the electric field state. And these eigenvalues are element of Z. So it goes essentially from -infinity to +infinity. The plaquette operator is the operator of the link operator around the plaquette. I will show a picture later. And this represents lowering and raising operators. So if I apply a plaquette operator on a state Pn, I lower it by 1 unit, so it goes to Pn -1. This is already the lattice Hamiltonian. You can take the naive continuum limit, sending the lattice spacing to 0, and you recover the U1 gauge theory Hamiltonian from the continuum. In addition to these operators, we have to fulfill the Gauss law. So if you have some electric field at a point N and an electric field at a point N-1, then the field flow between these 2 points has to be compensated by the charge. So this operator here has to give 0 on the state phi. So phi are the allowed states, and these are the physical states. And I implement this locally for all lattice points N. And here's the picture what we have. We have a torus where we have periodic boundary conditions in X and in Y direction. And if I take just a segment of this torus, so I take this segment here, then I have the plaquette. So I have link operators that go around this plaquette. And on the links, there live also the electric field operators. And on the edges, I can put charges if I want. Okay. This part of the picture I will explain later. Okay, so what I showed you is the Hamiltonian in the electric basis. And I told you that the electric field operator takes eigenvalues from -infinity to +infinity, which means that we need to truncate a theory. So instead of having the eigenvalues here going from -infinity to +infinity, I let them go from -L to minus capital L to plus capital L. And this L I have to choose. And if I am in the electric basis and I work at strong coupling, so G square, the bare coupling is much larger than 1, then I can choose this capital L to be order of 10, which is completely sufficient to describe the system and represents really the full U1 gate theory. The problem appears when we let G square going to 0, which actually corresponds to reach the continuum limit. In this limit, the truncation actually has to go to infinity to represent the U1 gate theory. And now this is impossible. I cannot have infinite resources, which means I have to live with a truncation. And on present day computers, if I think of capital L to be 100, this would be much too much, which means that with this simple approach, I would not be able to reach the continuum limit. One could think of replacing U1 by a Z2L plus 1 theory. And this would be a good approximation to U1. And I can live with these degrees of freedom. But then I have another problem when L is small, and I need L to be small to realize this on the quantum computer. We hit a freezing transition. So this is illustrated here. Please only look at the line down here. So only the x-axis. So this is plotted as a function of beta, which is 1 over G square. So beta infinity here is the continuum limit. And if I use, for example, the Z12 theory, approximating U1, then at some point I reach a freezing transition, after which the system doesn't change at all anymore, which again would mean that I cannot reach the continuum limit. Okay. And this is our idea now. What I can do the following. I can really mitigate or even solve the truncation problem. And the strategy is that even if I have a very large capital L, so a very large truncation, I can still have, and this would mean that I have a very fine resolution. I could only take 2 small L plus 1 degrees of freedom centered at the 0 state. So what does this mean? This means when I take G square to be much larger than 1, I'm in the electric basis and L can be small. And then the resolution, capital L, can be equal the truncation small l. When G square is much smaller than 1, meaning we are very close to the continuum limit, then I could still use the resolution capital L to be very large, so the resolution to be very fine, but still small l to be much smaller than capital L. And as I said, capital L plays then the role of the resolution and small l plays the role of truncation. And this is illustrated here. When I'm at G square much larger than 1, then I can use capital L to be 3 and 2L plus 1 would be 7. And I would have such a rather coarse resolution, which is fine in that regime. And I can use small l to be, for example, 1. So I only take 3 of these elements into account. And this I can repeat if I take a larger truncation, then essentially capital L corresponds to small l. If I go to G square much smaller than 1, then I can use capital L to be 6. So the resolution is 13. And so I really have a lot of segments. But again, the only relevant states are the one around the 0 states. So I can take small l to be 3, or let's say small l to be 2. And I explore only the region for the relevant physical states, which are centered around the 0 state. And the interesting question here is, of course, when I have G squared to be order of 1, what is then the interplay between capital N and small l? And I heard that also some lattice people are in the audience. This idea, unfortunately, doesn't work for Markov chain Monte Carlo, because this would lead still to large autocorrelation times. There's something in the chat. Is there a question, Rafaela? Don't hear anything. Yes, you can ask questions during the talk. And actually, I encourage you, and you can't unmute. Rafaela, can you let him allow to unmute?
Yes, 1 second.
Okay, thanks. And can you please have an eye on the chat such that we can receive questions?
Yes, you can unmute.
Hi, thank you. Yeah, thank you, Karl. So this is my first Quant Hep seminar, so I didn't know the protocol. My question was, when you say the 2L plus 1 degrees of freedom, are you referring to the electric field? The possible values that the electric field can take?
Exactly. So what we said, I can again not page, let me try again. What we said, so these are the eigenvalues of the electric field operator, right? Which in principle goes from -infinity to +infinity. And what we do is not this. This slide is gone. This is, I have to admit, something is really strange with my computer today. Yeah, it's here, yes. So what we do, instead of having these eigenvalues to go from -infinity to +infinity, we truncate them between -capital N and +capital L. Okay? This means that we have 2L plus 1 degrees of freedom for the electric field operator.
But if you do this truncation for the electric field, should you not also do the same for the magnetic field, or you do that later, I guess?
No, the magnetic field operator is different.
Oh, okay, all right, thanks.
Are there more questions? I see 2 things in the chat. Okay, fine. If you prefer, good. So Yasser is suggesting that we have the questions at the end, but I think I have some breakpoints in the talk where I ask you as a
yeah, so it's up to you, Karl. So it's up to you. Whatever you feel more adequate, please.
I think if people have immediate questions, they can simply ask.
Okay, thank you very much. So I would ask Sagar or Rafaela to allow people to unmute themselves and ask questions as per Karl's suggestion, please.
Okay, thanks a lot. So this is the general idea, and I hope you got it or you have questions on this.
Are you asking me? Sorry.
No. I ask in general.
Oh, general.
Okay, then let's continue. So I told you that we have the Gauss law, and Gauss law here is something very nice. Namely, Gauss law tells you that you have a set of equations that are constrained. You see that certain E-field operators, for example, this one, appear twice in these equations. So you can actually solve these equations, and this allows you to eliminate some degrees of freedom, some operators that you have. However, when you do this, you can imagine that you get complicated and non-local interactions, right? And therefore, what we also suggested is that we actually go to a different formulation, namely to the formulation of rotators and strings. And this is indicated here. So what we have is that we have rotators, which are essentially the plaquette. And due to gauge invariance, we only have to look at 3 of these rotators. The 4th one I can eliminate. And I can have strings. So this is, for example, the string in the x direction. It's just the combination of these 2 electric field operators. Okay. So we go from plaquettes to rotators, which are these operators here, and from the electric field operators to string operators, which are these lines here. And there is a relation, and the relation is written down here between electric field operators and strings. And this I have written down here just to show you that you can express really the electric field operators by the rotators and the strings. And here's the inverted version where I've written down how the rotators and strings are expressed in terms of the original electric field operator. Just for you to have a dictionary and to show that this is really one and the same formulation of the problem, just expressed in different degrees of freedom. Now, further simplification, if we don't allow external charges, we can set them all to 0. And then the electric field operators or the string operators commute with the Hamiltonian, which means that the string operator actually becomes irrelevant. And then the Hamiltonian becomes rather simple. So in the electric field, we have all the rotator states or the rotator operators. And in the magnetic part of the Hamiltonian, we have the plaquettes, where we eliminated one plaquette through gauge invariance. So, and therefore we have this term here, the product of the 3 plaquettes. Okay. And now comes the point that we can switch from the electric basis to the magnetic basis through a discrete Fourier transformation. So here's my Fourier operator. So this is a discrete Fourier operator where we have states nu and mu, and I sum over all the possible mu and u's in the Fourier transformation here from -L to +L. And what this Fourier transformation does for you is that, for example, if I have a Fourier transformation from the left and the adjoint from the right of the plaquette operator raised to a certain gamma, then instead of having a full matrix, I can diagonalize the plaquette operator. So I only have diagonal elements for the plaquette operator. So I work in the basis where the magnetic part of the Hamiltonian is diagonal, but the electric part of the Hamiltonian becomes rather complicated, but we can write down the expression. So the string operator looks like this, with coefficients that are known analytically. And we also know the square of this operator, again, with coefficients that we know analytically. So I go from a diagonal basis in the electric basis to the magnetic basis where the plaquette operator is diagonal. And we will see why this is good and why this is important. Yeah. So this is the Hamiltonian then written down. This is the electric part. It looks complicated, but it's implementable. And I will show you on the next slide how this can be implemented. We have these coefficients that we know, and we have this diagonal part of the magnetic Hamiltonian. So this bold R has the 3 components of the 3 plaquettes, but it is diagonal. So we have R1, R2, R3 times R1, R2, R3. And these are the cosines that come from the plaquette operator, just from the Fourier transformation. And to implement all this, what we do is that we use this raising and lowering operators, this V hat, which have for the electric part for the string operators have only ones on the off diagonal. So this then corresponds to a lowering operator. And for the magnetic part, for the plaquettes, we use the third component of the spin operator. And you can show that if you use this, you can fulfill the commutation relations that we started with from the U1 theory. So this is a true and valid representation of the U1 theory with the truncation capital L. Okay, do you have questions up to this point? Is it too complicated? Is it okay? Is it understandable? Shall I repeat something? If you don't raise your hand and say something, I will continue. All right. So, and then we did some test of this, and we did a test for only one plaquette. So we only have one plaquette in our setup. And if you only have one plaquette, then the observable that you can compute is the expectation value of the plaquette observable, which is nothing else but the Hamiltonian in the magnetic, which is nothing else but the magnetic part of the Hamiltonian in the ground state. Okay. This looks simple, but this is interesting already by itself, because you can use this plaquette expectation value to detect phase transitions. You can even use it to show the order of the phase transition. And just to say this, the same thing was used in the 1980s by Mike Kreutz in his pioneering work to show that you can use Monte Carlo methods to do calculations in lattice gate theory. And this really opened the field of the numerical simulations that we did, and where we reach today the physical quark masses on lattices that are as large as 100 cubed times 200, right? So this is one thing. You can use this to really map out the phase diagram of the theory, but it can do even more, namely it encodes the running coupling, which you can define as the bare coupling G square divided by the fourth root of the plaquette expectation value. And this was demonstrated in this paper here. And maybe just to say this for those who know, you can do a perturbative expansion of the plaquette expectation value, and then you can match this to a non-perturbative simulation. And this allows you to calculate actually the lambda parameter, which is the scale of your system when non-perturbative physics sets in. So this is a very important scale or parameter of the theory. Okay. No. Okay, and here we did now the experiment and looked at this truncation. So this is the plaquette expectation value measured when we use the electric basis. And this is the plaquette expectation value when we use the magnetic basis. And what you see here is that so this is as a function of 1 over g square, and the continuum limits is for large values of this 1 over g square, so towards here. And what you see here, if I use the electric basis, then up to roughly 0.5 or so, there's no effect of the truncation. So I choose small l to be 2, 3, 5, and 10, which corresponds also to large L. And you see, you can really represent the system very nicely. You don't see any truncation effect. However, if you go to the magnetic basis, towards the continuum limit, you see a rather large effect of the truncation. And this is what I was talking about in the beginning. And the opposite is true if I use the magnetic basis. I have large truncation effects for small values of the coupling, but I basically don't see any truncation effect when I go towards the continuum limit. So this means, yeah.
Can I ask a question? Why these for the L equal 2, you see a lot of fluctuations in the magnetic basis. This is due to the way you implement it. I mean, what is the reason for these oscillations?
These are just some numerical instabilities.
It's just that.
This is nothing physical.
Yeah, so it's just implementation. In fact, it's just numerical problem. Yeah.
Yeah. Okay. Thanks for just interrupting me. This makes me confident that somebody is following. and here we see now the effect how the electric basis and the magnetic basis matches or doesn't match. So if I choose a truncation small l to be 1, then I see again that in the electric basis, I go to the right point here. So this should go to 0, which is fine. And for very large values of 1 over g squared, it should go to 1. And you see it doesn't do it. And the opposite is true for the magnetic basis results. We go to 1, but then if we go to the regime where the electric basis is important, it doesn't reach 0 at all. This is for small l to be 1. If I choose small l to be 2, I see the same picture. However, now I see that these two curves here from the electric and the magnetic basis actually matches around g squared to be 1, which means I can start if I want from the strong coupling regime, so 1 over g squared to be small, g squared large, then I go up to around g squared equal 1, then I change the basis, and then I can continue and I go really to the small coupling regime and I can take the continuum limit. Okay, so this is really what we wanted to see, and we were really happy to see that this matching here happens already with a truncation of 2, at least for this U1 gauge theory. And you can also, so basically here, we know our results, what we would expect, because we have a single plaquette and we have the Hamilton operator and we can do exact diagonalization. And we thought, what can we do if we don't have these exact results? And for this,
can I ask another question? Sorry.
Sure.
I mean, the question, it's nice that you see the 2 points, the 2 transitions happening at the same point. You cannot test with L bigger than 10, right? I mean, my question is, the slope in the transition is always, I mean, it keeps exactly as it is, or does it change with L?
It would change. It would change. And I think, I'm not sure whether we did this, but I think for L equals 3, this would really be completely smooth.
Okay. So there's you in a way you have a problem with the continuum limit, actually, right? Because you don't know exactly the slope at the transition point.
We don't know exactly the slope at the transition point. We can just test that if we go from the electric to the magnetic basis and we change L, that we find really a smooth transition.
Okay, thank you.
So let me just ask everybody, whenever you ask a question, to please introduce yourselves.
Yeah, thanks.
Thank you.
Sorry, Jean Seixas. Hi.
Okay, so what I said, if we don't have any more exact solutions, then we have defined 2 fidelities. One is the sequence fidelity, the other is the Fourier fidelity. And the sequence fidelity is nothing else but looking what happens if I go from L minus 1 to L. What is the overlap of these? What is the overlap of this for a given capital L? And the Fourier fidelity is simply, I have for a given small l and capital L, I have my ground state wave function in the electric basis. Then I perform this Fourier transformation and I look at the overlap with the ground state wave function in the magnetic basis. And this is what you can see here. So this is the infidelity. So what I want is that this number should be very small to have really a measure of how well the electric and the magnetic basis works, and also how well the truncation works. And what you can see in this Fourier fidelity, the infidelity is very large, which means this matches not at all. Also for small values of g squared, this doesn't match at all. But if I go to this regime where I have this transition from one regime to the other, you see that I have indeed a very small infidelity. And I think this partly also answers your question. By looking at this infidelity, I can really quantitatively say how much there is an overlap between the state in the electric basis and in the magnetic basis. And if I reach 10 to the minus 4 or even larger, then I'm pretty sure that I have a very good overlap. And the same you can do with the sequence fidelity. And again, you see if you are in the electric basis, then this is rather good here. Here it goes crazy. And the opposite is true in the figure B, where you can see that for small values of G square, it goes crazy as a function of the truncation, whereas at small values of G square, this nicely converges. And D, I do not want to discuss here.
Sorry, again, another question. I see again here some oscillations. Do you have by any chance for L equal to 4 or 6?
I think it's 2, isn't it?
Yeah, this is 2. Yeah, but all the others are 3, 5, 7. Yeah. And at 10, again, you have these oscillations. I'm just wondering whether this has to do with the structure of the lattice itself. I mean, the fact that it has an even number of sites.
That's a good. So this is not the number of sites, right? This is the truncation.
Yeah, sorry. Yeah, exactly.
Okay.
But I'm just wondering why it happens only for even numbers.
My answer is I'm wondering too now, because this is exactly your observation that this is only for the even sites, which means that you have an odd number of degrees of freedom, right?
Exactly. Since I passed through this problem, that's why I'm asking this question.
Okay. I have to think about this.
Because then it might be an easy way to explain why this is happening here. It just has to do with the number, with L.
I think this is true, but this is not yet really an explanation, right? Okay, I have to think about this, but a good observation. Thanks. Yeah, it's true. Okay, and now comes the question, how can we actually optimally choose capital L and small l? And for this, we use this sequence fidelity. So the overlap that I get when I change from L-1 to L. And we did a scan here. So this is the truncation capital L in this direction here. This is the truncation small l in this direction here. And this is the infidelity of the sequence fidelity. So I want to have this small as possible. And you see that we actually have I think it's easier to see in small l, that we have for a given small l, I always have a minimum in capital L. So I can identify for any chosen small l, those values of capital L that gives you the minimum of the infidelity of the sequence fidelity. So I can really fix then for a given small l, the best capital L for my simulation, for my quantum simulation. And this table here gives you actually then the results that we got. So when you would start it with my initial Hamiltonian on basically the first slide, so you do a brutal truncation of the theory, and to reach a certain precision, let's say for the plaquette expectation value, then you see that for 1 over g square 0.1, you would need 27 degrees of freedom. At 10, you need already larger than 2000 degrees of freedom, and at 100, it's roughly more than 10,000. If you just approximate U1 with a Zn theory, and you change from the electric to the magnetic basis in order to avoid this freezing problem, then you see that in the electric basis, you still have this 27 degrees of freedom. Same for the magnetic basis at small values of g square. But in the intermediate range, you still have more than 1000 degrees of freedom. And if what we called here the scales at end truncation, meaning this display with capital L and small l, so taking the best numbers from this diagram here, then you see that also in the middle region, when g square is around 1 or 10 here, we still have 125 degrees of freedom, which is still a little bit too much, but we have reduced the number of degrees of freedom by a factor of 10, which is clearly an enormous gain in the computational costs and makes this actually practical for quantum simulations. Okay, we can add matter. We are using staggered fermions, so we have this staggered factor here, and we have a mass term, and then we just have the psi dagger psi operator. We can also introduce a kinetic term where we couple fermions at neighboring sites with this link operator. We can express the charge operator in presence of matter, and we can actually perform all the same transformations to the magnetic basis and this scaled truncation to obtain an efficient Hamiltonian, also in the case where matter fields are present. And this is what we find then when we have matter. So there we used an open plaquette with dynamical matter. And what we see here is again the plaquette expectation value as a function of 1 over g square. So here we use the elliptic basis, go to some value of g square, and then we match and go here. And what we see is that we have a dip in the plaquette expectation value. And this is this we think is a sign of a phase transition. So this is a negative fermion mass, which would actually correspond to a theta parameter of a topological term to be pi. So we think this is a topological phase transition here at theta equal pi, which you can also represent when you have a negative fermion mass. Okay, so this is really an indication of this, and you can kind of understand this as competing effects of the kinetic part, in the case matter fields are around, and the magnetic terms. So they really try to compete each other, and they introduce this dip in the plaquette expectation value. We actually get a negative plaquette expectation value. Okay. And we went even further, so we developed with the group in Innsbruck. You see the people here. This has appeared in PRX Quantum. We developed actually a circuit that could be run on a quantum computer. So this is in particular designed for a trapped ion device, but this can also be used for superconducting qubits. And I just wanted to show you that we have developed a protocol for this to really run this problem on a quantum computer, and we can simulate this. So we did some variational quantum simulation on this to prepare for some actual quantum computation. And here are the measuring points. And you see that with this protocol, we again find this dip in the plaquette. The plaquette becomes negative. And as I said, we think that this is an indication of a phase transition at negative fermion mass. But since this is just a single open plaquette coupled to matter fields, this needs to be confirmed by going to larger system sizes. But I'm pretty sure this is a phase transition. Okay, do you have questions up to here? Because the next part would be 3 + 1 dimensional U1 with topological term.
I guess I have a question. When you say that you're doing the simulations only for a single plaquette, so how many degrees of freedom do you have overall?
So for the periodic plaquettes, what I showed you in the beginning, I showed you this table, right? This is this one here. So these are the number of degrees of freedom. Or let's take this box here.
Oh, I see. Right, because okay, depends on your truncation.
Exactly. This depends on the truncation.
Right.
Yeah.
I see.
Exactly.
So I mean, I mean, the question would be that do you have any reason to believe that the results for a single plaquette would scale?
Yes, I would think if I have periodic boundary conditions, I would be rather sure because of translation invariance, right? Single plaquette is sufficient just to measure a single plaquette. For the open boundary condition, I don't have translation invariance anymore. But as I said, the plaquette expectation value is a good indicator for a phase transition. This has been shown in different models. For example, if you think of SU2 gauge theory at non-zero temperature, you can identify the phase transition with measuring a single plaquette. Of course, there will be finite size effects, but the existence of the phase transition you can demonstrate.
Okay, thank you.
Okay, other questions? Maybe I continue.
Yes, please. Thank you.
So what we did then is we were thinking of going actually to 3+1 dimensional gauge theory. So this is very ambitious. And what we wanted to do is to study this 3+1 dimensional U1 gauge theory, or also non-abelian, in presence of a topological term. And for this, we didn't actually find a derivation of the topological term in the Hamiltonian formulation. And we thought about this for a pretty long time, how this should come out. And the key was the anomaly equation. So if you look at the divergence of the chiral current, which is given here, then this is related to the topological term in this way here. And therefore, you can, through this divergence, you can actually derive the Hamiltonian form of the topological term. And this you do with a chiral rotation. So you rotate the fermion operator with e to the I alpha gamma 5. And then you get this mass term. So you have this alpha parameter in there. And this shifts then the Hamiltonian, if you allow a parameter alpha here in front of this divergence, to this form here. So you get the topological term and you get the mass term, which has this alpha. And then if you, now we translate this with theta, and theta is alpha over 2, then if you have a negative mass term here, and theta equals 0, this would correspond to a positive mass term, but at theta equal pi. So here would be a theta half. Okay, so this is what I meant, that if I see a phase transition at a negative mass, at a negative fermion mass, this corresponds to a phase transition at theta equal pi if I would have a topological term. Now in 2+1 dimension, this is not so easy because we don't have a continuous divergence here, but we only have a parity symmetry, but the same statement would be true. I hope. This is our knowledge at the moment. So, and then we implemented this. This is, if you want, then the topological charge operator with the theta parameter here. And you see this is a combination of the electric field operator and the link operator, but we have derived this in the paper. There are alternative ways to derive this, for example, from the transfer matrix, which we also put into the paper, and the theta term as a perturbation. And what we then did is we looked at the single periodic cube. So we look at this cube here, and we have, due to periodic boundary conditions, we have links that we have to consider here. So these two balls are repeated here. So messages, we looked at a single cube, and we added this topological term. Okay, so then we have three terms in the Hamiltonian. we have again the electric field operator, we have the plaquette operator, and we have this topological charge. And as observables, we have again the plaquette observable, the expectation value of the magnetic part of the Hamiltonian. We have the electric energy, which is the expectation value of the electric part of the Hamiltonian. We have the topological charge by measuring this topological charge operator, and we have the electric fields. And what we did here, just to demonstrate that what are the effects of this topological term, we have chosen here an exact diagonalization because we found that in this setup, the number of degrees of freedom are becoming too large to implement this on present-day devices. But we wanted to see the effect, and we saw something. So this is the plaquette operator as a function of theta, and this is normalized such that if there is a phase transition, it should happen at around 0.4 and minus 0.4. And what we see, if we have a very small value of beta, beta is 1 over g squared, so we are in a strong coupling limit, then we see actually signs of a phase transition indicated by these peaks here at roughly the right values of this theta. And if I make beta larger, so going to smaller values of g squared, then this phase transition is weakened and you only see indications of the phase transition. So it seems that for some critical value of beta, this phase transition might vanish. You see this also in the topological charge expectation value, where for small values of beta, you have really sharp transitions when you change theta at around minus 0.4 and 0.4. And if you increase beta, then these sharp transitions vanish and you see a smooth behavior of the topological charge. And the same is true for the electric field, where again, for small values of beta, you have very sharp transitions at exactly the same values. And if you increase beta, then this is smoothed out. So I think this is actually the first time that these indications of phase transitions for the U1 theory in 3+1 dimensions was found. So we are pretty proud of this. And then we asked the question, what could be the order of this phase transition? So what we did, since we have exact diagonalization, we have access to the energy spectrum. And what we could see, we followed the ground state energy as a function of theta. And at around the point where we saw this very sharp transitions, we see an avoided level crossing. And an avoided level crossing would mean that this is a second order phase transition. So for the first time, we could not only find indications of this phase transition, but we conjecture that this is actually a second order phase transition. And it would be very nice to confirm this now, for example, using tensor networks on larger lattices. So for example, Simone Montangero, who cannot be here today, he has developed an algorithm with these augmented tree tensor networks. And it would be very nice if we could, now that we have this formulation of the topological charge term in the Hamiltonian, to check this. And this would be really, really nice. And of course, we would like to go to the Coulomb phase and explore the phases actually that are indicated here. What is the nature of these phases? Okay, this brings me to my conclusion. What I wanted to show you today is how can we implement and formulate topological terms for lattice gauge series in the Hamiltonian formulation, and how do I quantum simulate or do tensor network calculation for these theories. And I showed you the 2+1 dimensional gauge theory with and without matter. And I showed you that we have developed really a resource efficient formulation which works for both quantum simulations and tensor network calculations. So you can use this formulation in both setups. And this allowed us to perform already computation at all values of the bare coupling, which we demonstrated at the example of this 2+1 dimensional QED. And we found indications of a phase transition at negative fermion mass, which we interpret as a topological phase transition. this whole setup is this whole setup of switching from electric to magnetic basis and using this scaled truncation can be straightforwardly be generalized to higher dimensions, which means that we are actually ready for simulations of these gauge theories in 2 and 3 space dimensions with topological terms, which is nothing that the classical computations can do. So this would be something very nice to demonstrate on the quantum computer. Yeah, and this is the outlook that at least I'm thinking of doing this. So to use this setup to perform classical calculations with tensor networks, but also quantum calculations to use a real quantum computer for this. So thanks a lot for your attention and also already for the questions that were asked, but of course I'm open for further questions or comments.
Thank you very much, Karl, for this very nice talk. So indeed, there was already some questions. My colleague and co-organizer, João Seixas, will kindly manage the question session. So João, I give you the floor, please. He already also intervened during the...
Thank you.
Very good.
So questions, I'm on the side, so I'm not looking yet at the
I can check the chat, but I think so. There was.
But we are also live streaming to.
I can check that if you want.
Okay, okay. So more questions.
There's something in the chat. No, there are 2. No.
Periodic boundary conditions when taking a torus while defining fermions. We still have a torus, but in some sense a shift.
Sorry, can you repeat the full question?
I had a small question. We were considering periodic boundary conditions when taking a torus while defining fermions. Do we still have a torus, but in some sense a shift?
So the example I showed was for open boundary conditions, but if I would have periodic boundary conditions, we would not go away from the torus. This would stay the same.
Yeah.
Yeah. I simply identify the point when I go to the last lattice point to the right neighbor with the first lattice point.
Is it possible to use a configuration dependent coupling such that the theory, locally the theory is 1D? Can we use a locally adapted truncation resolution to keep Gauss law satisfied?
This I don't see. This I don't see. So what do you have in mind exactly?
I don't know. This is a YouTube question, Domenico Pamarico.
But I don't see this, that we can do this locally.
Yeah. David, Shaykh?
Hello, thanks for the nice talk, Karl. I had a question maybe elaborating on the resource efficient part of the classical tensor network calculations, where, not having done this myself, I hear people tell me that memory requirements rapidly become an obstruction for tensor network calculations in higher dimensions. And I was wondering if that would still be an issue in your formulation if you were to go beyond these single plaquettes and off to larger lattices, or if this formulation really solves that memory consumption more generally.
I would say yes. This was exactly the aim of this work, that we don't need so much resources, in particular also not memory. I think this can really help, but I also have to say what Simone is doing is really impressive. I cannot remember the exact numbers, but I think he went already to lattices like 32 to the cube. Huh? And this is all through this trick of this augmentation, such that you only combine 2 layers essentially of your lattice through the tensor network.
That does sound promising. Thanks.
Yeah.
Thank you.
Also something critical. This, of course, needs to be much more tested, whether it gives the right results finally.
What about leaving U1? I mean, can you go to, do you see a way of going to other groups than U1? I mean, leave QED basically. I was just thinking of the SO3 model. That's one where there are interesting things happening, the Georgi-Glasgow.
So not SU3, but there are 2 papers that really have implemented SU2 for the gauge fields. There's also a paper from the Waterloo group, but they have integrated out the gauge fields. So when you have the gauge fields in the game, you can do it. These people have shown that you can compute the plaquette for an SU2 theory, but this has to come with the price that you have to work out all the necessary Clebsch-Gordons, and the formulae are really becoming extremely, extremely complicated and long. This is something frightening, and you don't want to really implement this. We ourselves, we are thinking on a completely complementary way of doing this, but this is much too early to say whether this has a chance to work. But in principle, the setup is there. In principle, the setup is there, and you can do this also for SU3.
Okay, thank you. Any further questions?
Well, actually, I have a general question. So I know at DESI you're starting a program on quantum information, quantum computation, quantum technologies, and yourself, Karl, you've been collaborating with colleagues from quantum information. This is a general question: how you see this interface and the potential of quantum simulation, quantum computation to address these high energy physics problems? What's your view, please?
So which problems are you now referring to? The theoretical one or the experimental ones?
I meant the theoretical ones. Sorry, I should have specified. Sorry.
Well, I think we are still very far away from for simulating lattice QCD, right? I think we are more in the area in the era of Mike Kreutz in the 1980s, where he studied SU2 lattice gauge theory on a 4^4 lattice and showed that it is possible to obtain some results. And we have to realize that it took basically 30 years until we came to the point that we could say we have simulations at physical quark masses. We don't have to do chiral extrapolations. And we are now, after 40 years, we are at a point where we can simulate really large lattices of, as I said, 100 cubed times 200, and which brings us really close to the continuum limit. So if I think of this time span, then yes, it will take a lot of time to realize a generic quantum field theory like QCD on a quantum computer. But on the way to that, we can look at very interesting systems like this 2+1 dimensional QED, or as Yasser mentioned, we can look at non-abelian gauge series, and we can really address questions that we could not address before. Think of adding this topological term. You could really simulate and look at physics in the presence of a topological term, or we could look at physics by adding a non-zero fermion density in this model. So we could really try to understand what is the physics as a function of non-zero chemical potential and temperature. Or in addition, we can think of real-time simulations of these systems. So I think of a lot of possibilities on the way to lattice QCD. So to phrase this differently, for me, at the moment, actually the way is the goal. The way to go to lattice QCD and learn all these things from quantum computations. And my time span is really 30 to 40 years. I mean, it's not my time span personally, but for going to lattice QCD at physical quark masses and really doing some very, very new things.
And yet you have already some results on phase transitions, which are rather impressive. I mean, Michael Kreutz took a long, long time to discuss the question of order of phase transitions, while you seem here to have a much better handle of that already now, which is rather impressive.
Yeah, so this is something what both tensor networks and also quantum computations brought into the game. This is avoided level crossing, because you really get the spectrum, right? And also you have different observables. For example, you have the entropy. right?
Yeah.
You can measure the entropy, and the entropy is a very good indicator for a phase transition and also for the order of the phase transition. So these new developments have really brought in new observables, new looks at the problems that we are addressing.
Thank you.
Also, I have to say, I didn't talk about this today, but by doing these quantum computations, you learn to know all the nice features of quantum computers, namely that they are very noisy, that they sometimes break, and so on. So on the way, we have also developed methods and algorithms for completely eliminate readout errors. And also we have worked on algorithms to look at the expressivity of quantum circuits. So we have a method, if you give me your quantum circuit, we run it through our machinery. We can tell you which of your gates are redundant. And this is also something I hope that on the way to lattice QCD, we find more of these algorithmic and methods advances.
Yeah, thank you. Any further questions? Well, if not, we thank you, Karl, again for this very nice seminar. And now I'm not sure whether Yasser is still on online.
Yes, I'm here.
So you can talk a little bit about the series.
No, I can only repeat the pleasure and honor that was to have Karl here and to listen about this very nice work he's been developing. Thank you once again. Thanks also to the audience, to all the participants here and on YouTube. And I think, Rafael, you can please share the screen to announce the session of next month. So on the 3rd of November, we'll have Jesse Steller from MIT talking about quantum-inspired algorithms for collider physics. And finally, I just want to thank also the organizers. So Andres Ambainis, João Seixas, who is here with us, Simone Montangero, and also special thanks to Rafaela and Sagar, who make sure all these logistics in Zoom and YouTube works smoothly. So thank you very much, everybody, for your help and your participation. Special thanks to Karl for this very nice talk. Thank you very much and see you next month. Bye-bye.
It's a pleasure. Thanks.
See you.